Hi, welcome to Lesson 5.5, Making Connections, Exponential Models. The goal of today's lesson is to solve problems arising from real-world applications by applying a mathematical model and the concepts and procedures associated with the derivative to determine mathematical results and interpret and communicate these results. That sounds easy enough? So I'm just going to go through one example here. There's other wonderful examples in the textbook that you can read at your own leisure. And so the example I'm going to look at is using Newton's law of cooling. And the equation for Newton's law of cooling is T equals A plus T naught minus A times e to the kt. A is the surrounding air temperature, or the temperature of the surroundings, which is air. T naught is the initial temperature. K is the characteristic of the material of the body, or the scale factor, if you would. T is the time, and this capital T is the final temperature. So, imagine yourself in a steel mill, and rod steel is made, and when it's made, it is at 900 degrees Celsius. And it is cooled then by forced air at a temperature of 20 degrees Celsius. The temperature of the steel after 1 second is 400 degrees Celsius. Now that's some fast cooling. So what we want to do then is we want to decide or determine when the steel will reach a temperature of 40 degrees Celsius. So we want to take a little inventory of the different things that we have. So we see that we've got 900 degrees Celsius. It's cooled by forced air at a temperature of 20 degrees, and after 1 second the temperature is 400 degrees Celsius. So for this situation, let me see, we've got T is 400 degrees, we've got T naught, which is 900 degrees, we've got the surrounding temperature, which is the air, so A is 20 degrees, and we know the time of this little portion of it is 1 second. So what do we have? We've got the temperature, the final temperature here. 900 is the initial temperature. We've got 20 degrees for the air, and 1 second here. So the only thing we're needing to find here is K. Now the reason why we do this, we have all the information we need now in order to find what K is, and then once we know what K is, we can then attack this problem to find how long it'll take the temperature to reach 40 degrees Celsius. Okay, so this is sort of like a two-step problem. Well, it's actually exactly like a two-step problem. So the final temperature is 400, so we're going to have 400 equals A, which is 20, plus the initial temperature is 900, minus A, which is 20, e to the kt, and t in this case is 1 second. So we can just have to work that out a little bit. So 400 minus 20, we might see that would be 380. 900 minus 20 is 880 times e to the k. Now we need to find what k is, but it's way up there in the exponent. So well, first of all, let's get rid of this 880 from that side, so we can divide both sides by that. So we got 380 over 880 equals e to the k. We still need to find what the k is, so quite usefully, or conveniently I guess, we could perhaps take the ln of both sides. Here I am ruining all your chances to do some deep critical thinking. And we take the ln of this side here, and using the power law, this k can come down in front. And quite nicely, ln e is 1. So k equals ln of 380 divided by 880. And when we divide that, we get basically 38 divided by 88. Take the ln of that, and we get a k value of negative 0.8398. Okay, so we can use that to then find how long it's going to take now for the temperature to reach 40 degrees Celsius. So instead of using T as 400, we're going to change that to 40 in this formula, and then just go ahead and do everything else and find T. So I'll do this over here. So we got 40, which is the final temperature, equals 20, plus, again, 900 minus 20, e to the negative 0.8398 T. And we'll just do a little bit of rearranging again, subtract 20 from both sides, so we get 20 equals 880 e to the negative 0.8398 T. Then I suspect we could probably divide both sides by 880. And while we're at it, let's take the ln of both sides, bring down the power. So we do ln of 20 over 880 equals negative 0.8398 T ln E. Ln E will just disappear. Then we'll divide both sides by the coefficient of T. So we'll have T equals the ln of 20 over 880 all over negative 0.8398. And here's a great opportunity for a little bit of mental math. So you can do 2 divided by 88, take the ln of that, divide by negative 8.8398, and you would get something like 4.506. So the time would be approximately equal to 4.5 seconds. Sorry about that, I missed the last little step here. Okay, so that is the time it takes steel that starts out at 900 degrees Celsius to cool down to 40 degrees Celsius. So if you really wanted to touch some wrought steel that's fresh out of the foundry, you would only really have to wait for 4.5 seconds before it was cool enough to touch without burning your hand off. So that's not too long to wait. Now let's use some of this information to see what the rate of change is going to be, the rate of change of temperature at that time when the temperature does reach 40 degrees Celsius. So why don't we start off with the formula. And we'll put in the values later, but we can take the derivative of this. So we can do T prime equals, and now when you take the derivative of a constant with respect to T, it's just going to disappear. Then we're going to have T naught minus A times e to the kt times k. And so then we can plug in all the values that we want to use, and I'll bring this k to the front. So you get negative 0.8398 times 900 minus 20, so we'll do 880 times e to the negative 0.8398, and then instead of times t, we're going to multiply by 4.5, because that's the time when the rod steel is at 40 degrees Celsius. So that T prime of 4.5 is then, I'll just do one more step, not that we really need to, e to the negative 3.7791, and then when we calculate all that, we will see that that is negative 16.88 degrees Celsius per second. So therefore, using the $75,000 ellipsis, approximately negative 17 degrees Celsius per second. Okay, so that is the lesson. Thank you so much for spending all your hard-earned time watching this and paying attention. Your work here is at the bottom. Please complete these. Also, please read the examples in the textbook, because they will also complement this lesson by showing you other examples of different types, which will also help you work through these problems. And then all you review are these. Make sure you review the graphs of ln x, e to the x, ln of e to the x, and e to the ln x, etc. And their constraints, restrictions, etc. And the review from the review section 3 to 6, 7a, and 8 to 15, along with a few other questions from earlier sections. Okay, so thank you very much for your attention, and your time, and your patience. And we'll see you in class.